So let's start our next lecture on SA, and this is part 3 of the 3-part lecture on SA. And again, this is lecture 65 of my optimization series, and I am Dr. Ranjan Ganguly. Now, in this lecture, I'm going to discuss how the design variable moves around in the design space. Now, we saw that SA moves to a neighborhood point using a random move. And we will see that random numbers are involved in this move. Now, there are a few things to keep in mind whenever a new point is generated. One is that any new point generated should permit you to have small random changes, and also it should permit that all points in the design space should be reachable. So these are some aspects to consider. You also keep in mind that if you are dealing with a constraint optimization problem, then any new point you are selecting in the design space should satisfy the constraints, and of course the starting point x0 should also satisfy the constraint. That is, we are assuming that all the points are in the feasible region, and in case you are dealing with a constraint optimization problem, you may need to consider using some kind of penalty function here to enforce this particular rule for the problems. Now, a possible update formula could be that xi plus 1 is xi plus du, where u is a vector of random numbers in the range -1 to 1. D is a diagonal matrix which gives the maximum change permitted in each design variable. So this is a simple rule here. Here I'm using I in the place of the usual K we use here because that's quite typical in SA. And this rule will essentially let you move forward in the design space. Now, this D itself keeps getting changed. So once you have taken a new point, moved around in the design space, you change D also. So di plus 1 is updated using this formula here, where you essentially have a weight here, you have a damping constant, and R is a diagonal matrix. So again, the weights are given here, the damping constant, and R is a diagonal matrix, which includes the magnitudes of the successful changes made to each design variable. So this formula will make sure that the D matrix keeps changing as the design progresses. Now, if you are using these kind of update rules, there needs to be a slight modification to the probability of accepting worst solution. For example, the probability is slightly modified here. So T is replaced by TD, or we can say that delta F is replaced by delta F by D, where D is the mean step size. And delta F by D measures the effectiveness of the change made. Now, in many cases, the SA algorithm is good for discrete problems. For example, the traveling salesman problem, scheduling problems, and so on. And in those cases, if you have integer design variables, for example, you can obtain new points using this formula here. So xi plus 1 is xi plus u. So this is an example of a random search, and u is a vector of random numbers in the range -1 to 1. So essentially you are seeing that you are at some feasible point xi, you are perturbing this point slightly in a random manner, and you are creating a new point xi plus 1. Of course, you need to make sure that this xi plus 1 satisfies all the constraints in the problem, so it is in the feasible region, and also it satisfies any move limits which are there in the problem. That of course can be enforced by the fact that you create random numbers such that this whole thing lies within the particular move limits. So we see that SA is actually a very simple method in terms of programming. There is a lot of flexibility and robustness built into this method, and it's a good global search method because We saw one of the advantages of this method is that it tolerates an increase in the objective function to get to the global minimum. Some cases you can consider this philosophically also, that sometime you may need to actually go up to go down or go down to go up in life. So this particular situation of the non-linearity of the actual world is pretty much solved to some extent by using the SA method. We also see that it is conceptually simple. It has built-in heuristics to escape the local minimum traps. Now, when to use SA? I would say that if you look at the literature, most of the time it is being used for problems where you have nonlinear functions with multiple local minimum points, and also for non-differentiable functions. It's also used for intractable problems where you have discrete design variables. For example, I mentioned the traveling salesman problem and so on. So again, this method takes a lot of time. It may not give a very precise optimal point. It may give a rough optimal point, but for many practical situations, such an optimal point is very usable and very desirable. Now, the problem of this method is based on its fundamental physical thinking, which is that the annealing process has to take place very slowly. So this is one of the issues in metallurgy and material science, that you need to cool this particular material in liquid form very slowly, excruciatingly slowly. And therefore, this method becomes better and better depending on how slowly you are going to bring the temperature down from the initial temperature to the final temperature. And now translating this into actual computational world, what happens is that it would take a lot of computation time. So if your function calculations are computationally expensive, then this method is going to become very computationally expensive. Now, just like all heuristic approaches we discussed before, for example, genetic algorithm, and we are going to discuss later, for example, particle swarm, ant colony, and so on. All these methods depend on these parameters which are present in the problem. So you see all kind of parameters being present. And the selection of these parameters is essentially an art and plays an important role in the algorithm's convergence. And one of the issues with all these methods is that the algorithms would be highly problem specific. So if you are working on a certain type of problem, you may need to tweak your method and your parameters so that you get a better performance for that particular problem. Now there are many references if you want to further read on this particular method and check out some of these papers and books. So we will end this topic here of SA. It is interesting because it is a departure from the genetic algorithm type of method. We will again return to a similar biologically inspired method in the next video and in a further video, which is the particle swarm and then the ant colony. And you will see one of the differences in this method is that it actually deals with one point. Of course, you can generalize this to a population, but the way this method is propounded in its basic form, it essentially uses a point xk and then it moves to the point xk plus 1. So this method is capable of moving around in the design space in a slow and steady manner, and after some time it is going to get to a converged solution. Now, very often this method is recommended for scheduling problem, integer problems, discrete problems, traveling salesman problem, and so on. So again, I will end this lecture here. I will see you in my next video when we will discuss the particle swarm optimization.